Uh, Hello everyone, and today we'll be talking about variational autoencoders. So first let me start with first the acknowledgement. So a lot of material that I'm going to talk about today is based on these two tutorials and blogs, a lot of ideas from here. And the disclaimer which I want to begin with is that, so this is a slightly tricky topic because it's like a marriage between neural networks and graphical models, and there are multiple perspectives from which you can approach variational autoencoders or try to understand them. So you'll have to be a bit patient, and the entire picture would become clear only by the last slide or last but few slides, right? So just be patient. I'm sure by the end you'll understand everything, but we'll go through a lot of intermediate steps where I'll just leave the story at an unfinished point and then come back to it later and so on, right? So before we get into variational autoencoders, just a reminder that over the past few weeks, we have been looking at generative models, where the idea is that you're given a random variable x, where x typically belongs to Rn. So x is equal to x1, x2 up to xn, right? And we're given a lot of training data containing instances of x, right? So you have some n training samples given to you. And what we are interested in is learning the joint distribution of x, right? And what that means is that for all assignments to x, we are interested in learning this probability. And the way we go about it, this is now the standard recipe for a generative model, and I'll try to relate it to what we had done for RBMs, and we'll do a similar recipe in the case of variational autoencoders also, right? So what we do is that for all the training data that is given to you, for all the n training samples that we had, we want to maximize this quantity. And this makes sense because I've told you that this is what the data looks like. Here are some instances for this data. So if I'm assigning probabilities to these instances, I better assign high probabilities to them, right? I better maximize the probability to the instances that I've already seen in the training data, right? That makes sense. Now the question is, what is this optimization problem with respect to, or what are the parameters of this objective function or this optimization problem, right? So that's the question that we need to look at. So we looked at a similar formulation in the case of RBMs, where what were the parameters of this objective function? This gives me even more incentive to release the RBM assignment. You guys know it, just say it, right? What did we do to P? What did we express it as? Remember the energy function, right? So we had expressed it as an energy function, and what were the parameters of this energy function? W, B, and C. And of course, the function also takes in xi, right? Because you want to compute the probability of x taking on the value xi, so you better take xi as the input, right? So these, what we had done is, this is known as parameterizing the joint distribution using certain parameters, and the parameters were W, B, C, and then our optimization was with respect to these parameters, right? Is that clear? Right, so that's the standard recipe that is often used, that you're interested in a joint distribution, you want to learn the parameters of the joint distribution, so you come up with a parametric form for it, and this is the parametric form, the energy function which had these parameters W, B, C that we use for RBMs. And now the optimization problem is maximize the log likelihood of the data, this is the data, and the parameters of the objective function are W, B, C. Is that fine? Okay. Now let's look at a more simple case, right? That suppose, again I'll take the same case, that I want to maximize the log likelihood of the data that is given to me. And now what I'm going to assume is that this data actually comes from a Gaussian distribution, multivariate Gaussian distribution, and I'm also going to assume that the covariance matrix is identity. That means I don't really need to learn anything in the covariance matrix. Now for a Gaussian distribution, what are the parameters? Mu and sigma, of which I have taken sigma off the plate, right? I have said that sigma is, I've just assumed that it's I. Now can you tell me what will this object, what are the parameters of this objective function? What do I need to find such that the probabilities are maximized for the given data? Mu, right? Not sigma, because I've just simplified it by taking sigma off the plate, right? Now that's one way of approaching this problem. The another way of approaching this problem, which is something similar to what we did in the case of RBMs, is I say that don't take mu as a parameter. Assume that mu itself is some function of your input. Okay, so it is say theta 1 x1 plus theta 2 x2 plus so on. In general, I can just write it as it's some function of your input with the parameters theta, right? So express mu as a parametric form itself, right? We introduce some parameters and we also have the random variables themselves, right? Because we are interested in computing a particular assignment, so you better have the random variables in the equation. Does that make sense? Okay. Now if I do this, what should I optimize with respect to? Theta, right? So now my optimization problem becomes that instead of mu, I have expressed mu itself as a function of theta, and now I want to find these thetas, okay? And in particular, this function can be as complex as you want. It can have as many parameters that you want. So do you know of any such complex functions? Neural networks, right? So this is one recipe that we are going to look at today, that you are interested in learning a joint distribution. You assume certain parametric form for that distribution, right? Or rather, you assume certain family for that distribution, that it comes from a normal distribution, it comes from a Bernoulli distribution. It's not any arbitrary distribution, but you say it belongs to a certain family, and we are mainly going to focus on the normal distribution family. And as I said, the normal distribution has parameters mu and sigma. So the optimization problem should be with respect to mu and sigma, but we are not going to do that. We are going to express mu and sigma as a complex function of some other parameters, and then try to learn those parameters, right? So that's a very, very high level story or recipe behind what we are going to do today, okay? Is everyone clear with this? You get this indirect way of learning parameters of a probability distribution, okay? The distribution has parameters. The parameters are expressed as a function of some other parameters, and then you learn those parameters, okay? And this is very commonly done for learning generative models or learning the parameters of a joint distribution, okay? So with that background, so keep this overarching story in mind whenever we are talking about anything on the slides that I have, right? So this is the background story, and we'll be trying to fill in points in this story, right? Gaps in this story, okay? So before we start with variational autoencoders, let's start by revisiting autoencoders, right? So what does an autoencoder do? It takes an input x, it maps it to a hidden representation, and then tries to reconstruct the input from the hidden representation, right? So you have an encoder which does this. It takes the x and maps it to a hidden representation, and then you have a decoder which tries to reconstruct the input from this hidden representation. And this is a simple feed-forward neural network. What's the training algorithm? Backpropagation. What's the objective function? Squared error loss, right? So this is what we use. This is the squared error loss. So you have m training points, and the data is n dimensional. So for all the training points, for every dimension, you want to minimize the difference between the predicted value and the true value. We have done this tons of time in the course, right? So m is the number of training examples, and n is the dimension of the data that was given to you. Okay, this is what we have done many, many times in different applications, and in particular in the context of autoencoders. Now, what's the fun in this? I gave you an x, you gave me an x tilde. What's so great about it? I gave you some input, you just reconstructed the input and gave it back to me. What's so great about it? What did we do in the process? And I want you to use some terminology that we had introduced in the case of RBMs. There were two things that we were doing for generative models. One starts with A, the other starts with G. Abstraction and generation, okay? Okay, so now tell me, what's the fun in this? What have we done in the process? We have done abstraction, right? So we have been able to compute an abstract representation of the input. This representation is, first of all, compact, more meaningful. It ensures that the otherwise obvious differences between the inputs no longer exist in this latent space. So we had seen a lot of pics of sandy beaches with a blue sky in the background. They all looked different in the pixel space, but once you compute their hidden representation, all of them would come close to each other, right? So the fun lies in the fact that we are learning an abstraction for the input, okay? But RBMs were able to do something more than abstraction. What is it that they were able to do? Generation, right? So RBMs were also able to do generation. Can you do generation with an autoencoder? What does that even mean? What would generation mean? What is the input and what is the output? What's the input? Everyone? Hidden representation. And what's the output? An X, right? Whether you call it X tilde or X, it's an X, right? It's the image. If your network has been trained on images, given some hidden representation, I want to be able to reconstruct the image or some X tilde, right? So can you do this generation with autoencoders? If I want to do generation, which part of the network will go away? It's useless for me. After training, of course. The encoder part, right? When you say X, I assume you mean the encoder part, right? I don't need that. What is the input that I'll feed? H, and then the decoder will take over and it will give me X tilde, right? So this is what the question which I was asking, right? So when I say, can you do generation with an autoencoder? This is the situation that I'm talking about, that you remove the encoder. Now just feed an H to the decoder and see what it generates. So can you do this? Yes, right? I mean, what's the problem with this? I'll just feed some, H belongs to RD, right? I'll just feed something. Yeah, so in principle, yes. I mean, the mathematical operations you can do, you can take an H and try to reconstruct, but what would happen if you did this? You might get meaningless X's because you fed it. No, we did not, that's the whole point. We did not learn a probability distribution. We had asked a very similar question earlier in RBMs, and we'll get there. So, but I just want you to think about it, right? So all of you see there's some problem with this, but probably it's you're still not being able to make the connection to what the question that we asked for RBMs, right? So let's get there. So the problem is that H is actually a very high dimensional vector, right? So it's, think of this, I mean, I can't really draw high dimensional spaces, so I'll just draw this as the high dimensional space, okay? And now this space actually has many points, right? But actually the H's lie on a very small subspace in this large space. Why is it so? Where did the H's come from? X's. So X itself lies in a very high dimensional space. Of this high dimensional space, the actual images lie on a very small subspace, right? So the images are actually on a very small subspace. So it's quite natural that when you're trying to map them to hidden representations, they will also belong to a very small subspace in this large space, right? So now can you tell me a problem in feeding a H to the decoder and expecting it to generate an image from there? If I feed in this H, what will happen? It does not come from that space which it has actually learned, right? It's some arbitrary thing, so it will generate an arbitrary output. Do you get that, right? So the question which I am trying to ask is, of all the possible values of H is a vector in RD, okay? It's a d-dimensional vector. Of all the possible values of H, which ones can I feed to the decoder? What's the answer to that? And give me a probabilistic answer, or rather an answer in terms of probability. I want to feed the decoder those H's which are highly likely given the X's that I had seen during training. Then the moment I start talking about likely, what am I talking about? Probability distributions, right? So what I want to actually do is, I want a distribution over the H's, then I want to sample from this distribution and then take only the most likely H's, right? So in this case, the example that I showed you, this was the manifold on which the true H's lie. If I had learned a distribution, now it's very hard to explain this in a 2D case, but if I learn a distribution, then what I want is that it would have a very high probability for this region of the space and almost zero everywhere else. If I had such a distribution, if I sample from this distribution, then these are the vectors which I'm going to get, and that is fine, because my model knows how to deal with that. Does that make sense? Okay, so you see the problem with autoencoders. What does it give you? A hidden representation, but that's probabilistic versus it's, yeah. What's the other thing? Deterministic, right? So if I give you an X, it will give me the same hidden representation every time. Okay, it does not tell me a distribution over the hidden representations. Is that clear? Right? For a given X, if I feed it to the encoder, I don't have the encoder equation here, but this is what our encoder equation was, right? Wx plus b. And once my parameters are learned, no matter how many times I feed x to this equation, I'm going to get back the same h out. Right? This is a deterministic function. Okay? However, in the case of RBMs, we were actually learning a probability distribution. Right? We were learning that given an x, what's the probability distribution over the h space. Right? So I was able to do this. That means if I give you an x, every time you will not get back the same hidden representation. What you will get back is the probabilities of each of these hidden values taking on a value 0 or 1, and then you sample from that distribution, right? So what it will tell you is that, suppose there are 3 hidden dimensions, then what it will give you, what RBMs give you is this probability. Everyone remembers this, that this is the sigmoid function that we learn, and suppose it says this is 0.4, this is 0.3, and this is 0.8. And now the way you construct the hidden representation is that you sample from this distribution, right? And you decide to set the value to 1. If you're sampling from the uniform distribution, if the number that you get is greater than 0.4, you will set it to 0. If you get it less than 0.4, you will set it to 1, right? So that way you will get the distribution, get the actual value of h. So you're not getting a single h, you're getting a whole bunch of h's which come from this joint distribution. Does that make sense? Right? So as opposed to autoencoders, RBMs were actually giving you a distribution over the hidden representations, whereas autoencoders give you one fixed hidden representation for any given input. Is that difference absolutely clear? Please raise your hands if it is clear. Okay, good. Similarly, the decoder in the case of an autoencoder is also deterministic. If I give it a hidden representation, it's going to give me one x tilde back, right? It's not going to tell me that for this hidden representation, these are all the possible x's that I can generate. Now tie this back to the hidden representation story that we had, right? So hidden representations capture things like, is this image going to be sunny? Is there going to be an ocean in the background? Is the beach going to be white or sandy? Are there going to be trees? Are there going to be people, and so on? If I fix the values of all this, if I say that yes, it's sunny, yes, there's an ocean, no, it's not a white beach, and no, there are no trees, and yes, there are people. Even if I fix this latent distribution, there is a whole bunch of images which can come from this latent representation. It's not that there is a one-to-one mapping between this latent representation and the set of images that you can draw, right? For the same description, sunny beach with white sand and people on it, I can get many, many possible images. So what I have is actually a distribution over the input space given the latent representation and not a deterministic function, right? This probabilistic interpretation was captured by RBMs but not by autoencoders. Although both give you an abstraction, RBMs were also able to do generation, whereas autoencoders cannot do that. Does everyone completely get this part of the story? The difference, I'll not call it a limitation, but how autoencoders differ from RBMs, although you could potentially use both to learn an abstract representation. Okay? Okay, so now that's going to be the basis for the rest of the discussion. What we are going to look at now is something known as variational autoencoders, which have the same structure as an autoencoder, but instead of learning a fixed representation, they learn a distribution over the representation space, right? So now we can have a variational autoencoder, which will give us the two quantities that we are interested in, P of h given x and P of x given h. Now in the remainder of the slides, just to be consistent, so unfortunately when people talk about RBMs, they don't even use x and h, they use v and h, but for some reasons when they talk about VAEs, they use x and z, right? So for the remainder of this talk, to be consistent with the literature on VAEs, I'll also stick to x and z, but the mapping to RBMs is that x are the visible variables and h's are the, or the z's are the hidden variables, right? So just be comfortable with this transition, and at some places I might have again used h by mistake instead of z, right?